Swayam Prabha. Digital India. Educated India.
An important part of discrete mathematics is combinatorics, or simply counting various structures, various objects. So that's what we will now talk about. And we'll start with something you should already be quite familiar with, namely permutations and combinations. Let me start by talking about strings. So what do I mean by a string? It's simply, a collection, an ordered collection of objects from an alphabet. Okay, so alphabet is just a fancy word for a finite set. So here I'm calling it B. Each element in the set you could think of as a character, okay, or a letter in the alphabet. And a string, for this case, the alphabet is a set ABC, and A, B, C are the three letters in the alphabet, or the characters in the alphabet. And here is a string AACCA. It's length 5 string, so it has 5 characters in it in that particular order. Okay, so that's what a string is. But what is it formally? Formally, we could think of it as a mapping, a function from the positions to particular characters. So it's a function that maps the k positions. So in this case, k is 5. So 1, 2, 3, 4, and 5. Each of those 5 positions are mapped to an element in the alphabet. So here is another way to think of the same string. It maps 1 to A, 2 to A, 3 to C, 4 to C, and 5 to A. Okay, so that is what a string is. It's a function that maps positions to characters. Okay, the set of positions are mapped to the alphabet. And the combinatorial question here is, how many such strings are there? Once I fix the length of the string and the size of the alphabet. So the length of the string is k, the size of the alphabet I'm given is n. How many such strings can I construct? And you probably already know the answer. It's n to the power k. So you can think of each position in the string I could choose in n ways. So n times n times n repeated k times. So that's the total number of ways I can construct the string n to the k. Okay, this is something that grows exponentially with the length. Even if I fix the alphabet size n to be something small, say 2, you still have 2 to the k strings, which is growing pretty quickly as k grows slowly. And on the other hand, if I fix k to be a small number, say k is 2 or 3, talking about length 3 strings, and I let the alphabet size grow, it's only growing polynomially as the alphabet size grows. It's growing, say, if k equals 3, it's n cubed. Right? As n grows, it's growing only what we say polynomially. Okay, so that's just something to bear in mind. How do you formally see that n to the k is the answer? A simple way to do that is to prove by induction. So you will prove, you can induct over k, the length of the strings. You fix any alphabet size, so you fix n, and the claim is that, so denoting by alpha k the strings of the number of strings of length k over this alphabet, and the claim is alpha k is n to the power k. So to prove by induction over k, the base case would be alpha 1, strings of length 1. First that one character, so it's a single character, can be chosen in n ways from the alphabet. So alpha 1 equals n. And for larger k, you would inductively argue that any string of length k can be uniquely represented as a length k minus 1 string followed by a character. Okay? And your job is to count these pairs, a pair of the length k minus 1 string and a character. The length k minus 1 string can come in n to the k minus 1 ways by the inductive hypothesis, and the last character can come in n ways. So the total number of combinations of this is the size of the cross product here is n to the k. Okay, so you can fill in the details there, and that gives you proof by induction that the total number of strings of length k over an alphabet of size n is n to the k. It's simple enough, but let me actually illustrate it here with a tree. We will be talking about trees in more detail later. So here is what it would look like. So I'm interested in an alphabet of size 2 and strings of length 3. And to unroll the inductive proof we just had, the last character could be picked in two ways, A or B, and then I'm interested in picking the first prefix, a two-letter string to go as the beginning of this string. How many ways can I do that? Well, these are all the two-letter strings from this alphabet, so there are 4 of them. Of course, this you would again obtain inductively, but I've just shown it here directly, so you can have those 4 strings be AA, BA, AB, or BB, and to make them into strings of length 3, you already chosen the last letter, last character to be A, so you just append A to all 4 of them. So those are your 4 strings that end in A. And similarly, you have 4 strings, same 4 strings A, B, A, B, 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 but now appended with a B. So these are 4 strings ending in B, and these are all the 8 strings you have of length 3 over this alphabet. Okay, and here the n to the power k shows up as, so that's the total number of tables, strings here at the bottom level. And how do you get there? You could make a choice at each level. You could go in one of n ways, right? So n is 2 here, so you could have gone this way or that way. So there are n different ways you could have done the first step, n different ways you could have done the second step, and n different ways you could have done the third step. And those are the n to the power k ways you could have taken k steps in this tree to reach one of these n to the power k strings. Just one more thing to say here. This example we saw of binary strings is of particular interest. So binary string just means a string with alphabet of size 2. In the previous example, the alphabet was A, B, but often we would use the alphabet 0, 1 when we are talking about binary strings. And what we just now said is that number of length k binary strings is 2 to the power k, okay? Because n is 2. So yeah, here is an example. For instance, it's a length 5 string, binary string, right? And there are 32 ways you could have filled up this little string, and this is one such way. Now, interestingly, such a string can also be thought of as a set, more precisely a subset of a set of size k. In fact, let me define this particular set of size k, namely the first k integers 1 to k. I'll denote it using this notation, k in square brackets. So that is just notation for the first k integers. And so remember here I'm starting k positive integers, I'm starting counting from 1. And you could think of this string here as actually, so we saw the string is mapping k to 0, 1, right? This set k here to the set 0, 1. But you could also think of it as telling you of a subset of k. So this is very much the same way we talked about a predicate defining a subset. So this is actually a predicate, a function So string corresponds to a function to the alphabet being 0, 1. You could think of this as a predicate. The string could be thought of as a predicate over this set 1, 2, 3, 4, 5, and then it corresponds to a subset, right? So in this case, so subset formally is just all those positions I in the set K, where the string assigns a value 1. So this sigma sub I is just an alternate notation for sigma of I. Since sigma is a string, writing it as sigma sub I, the ith position of sigma, but it's technically the same as the value of the value that the function sigma assigns to the input I. And wherever sigma assigned the value 1, so in this case there are two of them, 2 and 5, those elements are part of my set. So if sigma is 0, 1, 0, 0, 1, S sigma is 2, 5. And there are, that's one of the subsets of this set. And since there are exactly 32 such strings, and every subset corresponds to a string, every string corresponds to a subset, there are 32 such subsets. Okay, so this is something very useful to know, that whenever I'm giving you a set of size k, it has 2 to the k subsets, including the empty set, which would be the all 0 string, as well as a full set, which will be the all 1s string. Now we get to permutations. So permutations are simply strings over some alphabet, with the restriction that the string contains every character in the alphabet and no character is repeated. Okay. So for example, if my alphabet is A, B, C, D, E here, this string corresponds to a permutation. It has all 5 characters appearing and no character is repeated. So it's a string of length exactly the same size as the alphabet. And since a string is just a function, a permutation is also simply a function. It's a function that maps the set n, so 1, 2, 3 up to n, to the alphabet, which also has a size n. And since no character is repeated, it's a one-to-one function, and since every character appears exactly once, it's an onto function. So it's a bijection from the set n to the alphabet, which is also of size n. Sometimes you would be interested in a more general notion of permutations, where the string could be shorter than the size of the alphabet. So in this case, if for example here you have a string of length 3, the alphabet is still the same, A, B, C, D, E. So here, not all characters appear, but every character appears at most once, so there is no repetition. In terms of functions, it is a one-to-one function. There are no two elements mapping to the same element in the domain, no two positions mapped to the same element in the codomain. So it's a one-to-one function. And the combinatorial question here is, how many such permutations are there? So how many length k strings without repetition exist over an alphabet of size n? I'm going to denote this number by p and k. So it's a function of the size of the alphabet and the length of the string. And you might already be familiar with the expression for p and k. So if k is greater than n, it's clearly 0, because there are no strings of length larger than n without repetition of characters. If your string is longer than the size of the alphabet, then you must repeat some character in there. So there are no such strings. So p and k is 0 when k greater than n. If k is less than or equal to n, then I claim that this expression here gives you the right count. And this expression is in terms of n factorial. So n factorial is defined as follows. So 0 factorial, I need to define 0 factorial here to handle when n equals k. So 0 factorial I define as 1, and for n greater than 0 I define n factorial recursively, or say inductively, as n times n minus 1 factorial. Okay? So simply, put, it is just the product 1, 2, 3 up to n, that is n factorial. So this is the claim that there's a number of permutations. How do you prove this? Again, you can use a simple inductive argument. This time it will be convenient to do induction on n. And for each n, you prove it for all values of k. So the base case would be n equal to 1. When you prove it for all values of k, always, k greater than n would be the easy case, and k less than or equal to n. In this case, there is only one such k, namely k equal to 1. And so P11 is 1. There is only one string of length 1. And that is indeed 1 factorial divided by 0 factorial. That's 1. That's the base case. And for the induction step, you can use the following argument. You could say, what is a string? What is a length k string without repetitions? Well, you could think of it as a length, you could think of it as first you pick, say, the last character of the string. You can do that in n ways. And then for each of those ways in which you pick the last character, the first k minus 1 characters, they form a permutation, but from the alphabet which excludes this last character. So it's a permutation of length k minus 1 from an alphabet of size n minus 1. And there are p n minus 1 comma k minus 1 ways of constructing such a permutation. And for, so you first pick a character for the last position n ways, and then you pick a compatible permutation for the first k minus 1 positions in these many ways. Okay, and by induction, you would already have the expression for p n minus 1 comma k minus 1, so you can plug it in and verify this holds. You could also do this induction in a slightly different way. You could say any length k string you could think of as first k minus 1 length string, but you pick that first out of all the full alphabet, right? So you can do that in pn comma k minus 1 ways, because you have all n characters from the alphabet to pick from. But once you have picked a k minus 1 long string, you have used up exactly k minus 1 characters, and you're left with n minus k minus 1 or n minus k plus 1 characters to pick from for the last position. So here, and again, you can plug this in into the plug the inductive hypothesis in here, and you would get this expression. Okay, so again, I'll leave it as an exercise to fill in the details. If you didn't notice, this n factorial divided by n minus k factorial is bound to be an integer. It's simply this factorial, right? N times n minus 1 all the way to, you just take k such factors. So n times n minus 1 all the way to n minus k plus 1. And that's what comes out if you plug in the definitions for n factorial and n minus k factorial into this expression. A special case of n k, so p and n, is simply n factorial divided by 0 factorial, or the following factorial n is simply n factorial. To illustrate forming these permutations, here's our example again. This time I'm using an alphabet of size 3, so that I can pick strings of length 3 permutations. So my alphabet is ABC. The first or the last position I can pick in one of 3 ways, and So there are n ways I could fill the last position. The next position I could fill in n minus 1 ways because I already used up one character, and then the next position in n minus 2 ways. The total number of ways I can do this is n times n minus 1 times n minus 2 for k equal to 3. Okay, so that's all I wanted to say about permutations for now. And